Hello, welcome to Advanced Composites. Today is the last day of the 7th week of this course, and yesterday we just started a new topic related to thermal effects in composite laminated plates, and in that context we have developed several equations, or actually we have gone ahead and modified several sets of equations to incorporate temperature effects. So, the first modification we did was that if there is thermal effect, then the Hooke's law relations, which are these, they get modified to these sort of relations. And here alpha 1 and alpha 2 are coefficient of thermal expansions of the material in 1 and 2 directions, and these modified relations relate stresses to strains in the system. And then we made these relations more general, and we said that sigma x, sigma y, tau x y are related to the strains from based on these relations. And here the important thing to remember is that epsilon x, epsilon y and tau x y, gamma x y, they are the actual strains which we may be able to measure if by putting strain gauges. So, they are actual physical measurable strains, while alpha x, alpha y and alpha x y times delta t, they are mathematical entities. So, what I was saying is that the relationship between the stresses sigma x, sigma y and tau x y and the strains gets modified in the x y coordinate system through these relations. And here the strains which are encircled in the red box, that is epsilon x, epsilon y, gamma x y, they are the actual measurable physical strains in the system, while alpha x delta t, alpha y delta t and alpha x y delta t, they are thermal strains, and basically they are mathematical entities to account for thermal effects present in the composite laminates. So, this is the first set of changes we have to accommodate to account for thermal effects, and these changes appear in the stress strain relations. That is the first set of changes. The next set of changes which we had discussed, and before we go to the next set of changes, how do we calculate alpha x and alpha y, gamma x y? It is if alpha 1 and alpha 2, which are the coefficients of thermal expansion in 1 and 2 directions of the material, they are known, then we can compute alpha x, alpha y and gamma x y through these relations. So, we can calculate that. So, what I mentioned earlier is that this is the first set of changes we have to account for when we are interested in learning about thermal effects. The next set of changes appear in the relations between N and M resultants, that is the moment and force resultants, and the midplane strains and midplane curvatures. When there are no thermal effects, then this is the governing relation, but the moment we have thermal effects, the relations between N, M and midplane strain and midplane curvatures, they get modified, and these are the modified relations which account for thermal effects. So, this is there. And to recap, so what we have is two additional terms, NT and MT, and these terms NT and MT are account for the temperature effects, and they are nothing but multiples of NT, N hat T and delta T and M hat T and delta T. And for purposes of completeness, we will define the how we compute NT. So, N hat T, and this we had developed the relation earlier, but I will just recap. So, this equals, so this is N T, and let us say this is in the x direction, then it is Q11 alpha x plus Q12 alpha y, and actually these are bars, plus Q16 alpha x y for the kth layer multiplied by the thickness of kth layer, which is zk minus zk minus 1. And likewise, we can also compute relations for nty and ntxy. So, nty is equal to, this is again zk minus 1, and these relations are q12 alpha x plus q22 alpha y plus q26 alpha xy for kth layer, and once again these are bars. Yeah, and in for the cross component, these are q16 alpha x plus q26 alpha y plus q66 alpha xy for kth layer times zk minus 1, and once again these are bars, and the summation is always from 1 to n layers. If there are n layers, so 1 to n, 1 to n, and 1 to n layers. So, this is how we define nt hats, and I will just write one expression for mtx, and using analogies you can have expressions for mty and mtxy also. So, mt hat in the x direction is equal to n summation from 1 to n q11 epsilon x plus q12 bar epsilon y plus q16 bar not epsilon, alpha x, alpha y, and alpha xy, and instead of thickness we have zk square minus zk minus 1 square divided by 2. And similarly, we can develop expressions for mty and mtz. So, this is the second change, that the relations between n, m and ABD matrices, they change and they get modified by the presence of this term, these terms. Okay. Then the next one is equilibrium equations. And what we are talking about is, when we are talking about the equilibrium equations, so the first equilibrium equation is del nx over del x plus del nxy over del y equals 0, and then we have second equation and third equation. When we are talking about these equilibrium equations, these do not change, because what these equations imply is summation of forces in the x direction is 0, in the y direction is 0, in the z direction is 0, and summation of moments around y axis, x axis, and z axis is 0. So, these three equations reflect these different equilibrium conditions. So, these do not change, because these are we are talking about forces. So, they do not change, and the boundary conditions, they also do not change. So, the only thing which changes is these relations and the relation between stresses and strains. So, if we account for these changes, then we can accommodate thermal effects relatively easily. So, now what we are going to do is, we will actually solve a problem, so that we learn through an example how these type of problems are handled. So, again we have a semi-infinite plate, plate. So, So let us say the top layer is 0 degrees and the bottom layer is 90 degrees, okay, and it is a free plate. So, it is a free plate, meaning that there are no restrictions on any of the edges of the plate. And the third thing is that this length is A and the width of this plate is very small compared to A, which is the length of the plate. The coordinate system, as we have always done, is located in the at the center, and the z axis is pointing downwards. So, given that this is a free plate, what are the boundary conditions? So, if you go back and look at the boundary conditions, each edge has to have 4 boundary conditions, and because this is a semi-infinite plate, we really care about this edge and this edge. So, what are the boundary conditions? The first one is that Nx at both the edges is 0, because it is free, so there are no external forces acting upon the system. Then Nxy for both the edges is again 0. Then there are no moments, external moments at the edges. So, Mx plus at both the edges is again 0. And the fourth one is that Qx effective, and the definition of Qx effective is what? So, at plus edge and minus edge is also 0, and we had defined what is Qx effective. It was Qx on the edge plus partial of Mxy with respect to y, and Qx is a function of y. So, all these entities on positive edge and all negative edge, they are 0 anyway. So, these are the things. So, these are the 4 boundary conditions. So, now the question is, if the plate experiences a temperature change of delta T, we have to find out its deformed shape. How do we find its deformed shape? So, we have to essentially find u, v and w for the plate once it has been subjected to a temperature of delta T. So, the first step is we do equilibrium equations. And when we are doing these equilibrium equations, we realize that del over del x is equal to d over dx and del over del y equals 0, because the plate is very long compared to its width. So, we say the first equation is dnx over dx is equal to 0. This is from the first equilibrium equation, and this gives us nx is equal to C1, right. But the plate is not being subjected to any external stresses. So, at x is equal to plus a by 2 or minus a by 2, its value should be 0. So, this is equal to 0 from BC. Okay. The second equation is dnxy over dx is equal to 0. So, this gives us nxy is equal to C2, and again from the boundary conditions we get C2 is also equal to 0. The third equation is d2mx over dx square equals 0. So, this gives us mx is equal to C3 plus C4, C3x plus C4. But once again, from mx plus and minus is equal to 0, we get C3 is equal to C4 is equal to 0. So, mx is equal to 0. And so, what it means is that when a plate of this type, unsymmetric laminate, if it is subjected to a temperature change, there will be no nx or nxy or mx inside the plate, because this is what it is telling us, and it makes sense because the plate is free. So, it does not experience any internal stresses because it is free to move. So, it will assume whatever deformed shape it has, and that is what these equations tell us. So, now our aim is to compute the displacements in the plate, and what we will do is we will use these relations and express these relations in terms of u, v and w, and then compute and find displacement functions. So, but before we do that, we realize that, so we use the ABD relations for nx, ny and mx. See, these are the three things we computed: nx, nxy and mx. So, we expand nx, nxy and mx in terms of u, v, w and delta t. But before we do that, we note that in ABD relations, A16, B16, A26, B26, D16, D26, B12 and B66 are 0 because it is a cross ply laminate. Also, so this is one thing. Also, we note that nxyt hat is equal to 0 and mxyt hat is equal to 0. And why is it 0? Because we look at the definition. What is nxy? Nxy is q16 bar plus q26 bar alpha y plus q66 bar alpha xy. Now, for a cross ply laminate, all the plies are either 0 degrees or 90 degrees. So, q16 bar is 0, q26 bar is 0 for a cross ply laminate. So, first two terms go away, and because the laminate is cross ply, alpha xy also for each layer is 0 because the layer is either 0 degrees or 90 degrees. If you remember, in the very beginning we said that if our material axis is aligned alpha 1 2 for for this material axis system is 0. So, because of these reasons, both nxy hat and mxy hat, the temperature components, they are 0. So, now we write an expression for nx. So, nx is equal to A11 du naught over dx minus B11 d2 w naught over dx square. So, these are the terms we have already developed for in case E and C and D, right. But now we will have an additional term related to temperature. So, that is minus nx times delta t, t and this nx hat. And so, this is equal to C1 and this is equal to 0, or actually let us call it 1. Then ny is equal to A12 du naught over dx minus B12 d2 w naught over dx square minus nyt delta t, this is hat, is equal to, yeah, so this is there. So this is equation 2, and nxy is equal to A66 dV naught over dx minus nxy t times delta t, and this is hat, but we said that this thing is 0. So this is, and this entire thing equals C2, and this is equal to 0. So essentially what it means is that V naught is equal to C3. V naught is equal to C3, because when I integrate this equation, V naught becomes, V naught is equal to C3 or C3 by A66, okay, C3 by A66. Now what does this mean? What it means is that the plate has the same, it could have the same displacement at all points in it, because it is a constant thing. So what that means is that if I am just moving my plate, suppose the plate is just moving at some uniform velocity, then it has some same displacement, hai. So not uniform velocity, it is just that, it is just a question of rigid body motion. So I can as well assume C3 represents rigid body motion. So suppose the plate is initially here and it just moves like this, so it is a rigid body motion. But if it just moves as a rigid body, nothing changes in the plate, right, nothing changes at plate. So the state of the plate in this case or this case is the same. So I can as well assume that this is equal to 0, because C3 represents rigid body translation. So we can just consider that rigid body translation as 0, okay. So these are the 3 equations related to n's, and then let us look at one more equation, m. So mx is equal to b11 du naught over dx minus d11 d2 w naught over dx square minus mxt times delta t equals 0. So this is equation 4. So these are the 4 equations, and then we can also develop expressions for my and mxy, and what we will do next is we will use these equations, because these are equations in u, w and v. We will use these equations to compute u and w. V we have already computed and we have found that v is 0. So we will likewise similarly compute expressions for u naught and w naught, and then we will like to look at the behavior and how these relations affect the shape of the plate. So that is what we plan to do going forward. Today's time is over, so we will continue this discussion in the next class. So till then, have a great weekend. Bye.